Hi guys, up to now we have seen different type of fault and what is the fault current and what is the fault MVA for symmetrical as well as unsymmetrical type of faults. In symmetrical we have seen triple L fault and triple LG faults. In unsymmetrical we have seen LG, LL and LLG type of fault. So in this lecture what we will do is we will focus our attention to solving few problems that have been based on unsymmetrical type of faults so as to get to know better how to tackle such kind of problems. So let us get started with our first problem. It is saying it is given that Vs1 is equal to Vs2 1 plus J0. Okay, that means Vs1 is equal to Vs2, that is 1 angle 0. Then positive sequence impedance Zs1, Zs2 are 0.001 plus 0.01. ZL is 0.006, J 0.06, base MVA 100, base voltage 400. Nominal system frequency is 50 Hz. Now VA is given as reference voltage for phase A, Vm cos omega t. A symmetrical three-phase fault occurs at center of the line I at point F at time t0. The positive sequence impedance from S1 to F equals this. Okay. Since fault is occurring at the midpoint, the impedance of the line will be taken as ZL by 2. That is 0.003 plus J 0.03 pu. And let me show you the diagram. Fault is occurring here. And the impedance from source 1 to F will be Zs1 plus ZL by 2. Zs1 plus ZL by 2 will be 0.004 plus J 0.04 pu, which is given in the question also. The waveform corresponding to phase A fault current from bus X reveals a decaying DC offset current. Okay. The thing is, whenever we will study about the fault current, there are two components, transient and a steady state. It is saying the waveform has a DC offset current that is negative. So this is actually transient current and in magnitude at its maximum initial value. So magnitude is maximum but the value is negative. Assume negative sequence are equal to positive sequence impedance. Zero sequence is 3 times positive sequence. Z2 is equal to Z1. Z0 is given as 3Z1. First question it is asking what is the instant of the fault. Now for transient and steady state we derived the current as IT0 e raised power minus RT by L plus Vm by mod Z. Here it will be cos of omega t minus theta. Theta will be tan inverse x by r, that is 0.04 by 0.004, which will be 84.29 degree. Now at t is equal to t0, when the fault is occurring, IT must be 0 due to current continuity. We are assuming no load condition in the system before the fault occurrence. So IT0 e raised power minus RT0 by L will be equal to minus Vm by mod Z cos of omega t0 minus theta. Now this is the decaying DC offset current. It must be negative, so negative sign is coming here, and equal to maximum initial value. For maximum value, the maximum value of this current will be Vm by mod Z because cos can be 1. So this should be equal to minus Vm by mod Z, which implies that the term inside the cos should be equal to 0 because cos must be equal to 1. That means omega t0 must be equal to theta. So t0 will be theta by omega. 84.29 into pi by 180 whereas omega will be 2 into pi into 50. So this will come out to be how much if we calculate 4 point, this will be 4.682 millisecond. So this will be the instant of the fault. Okay. So what the case that we considered while deriving it was the fault was occurring at t is equal to 0. But here we have seen a general case, the fault occurs at t is equal to t naught. Okay. So just you have to decode the language and nothing else, though the question seems a bit bigger, but the solution is not that much tricky. The next part of the same problem asks us to find the RMS value of AC component of fault current Ix. Okay. RMS value of AC component, that is symmetrical fault current. Now RMS value will be V by mod Z. Okay. V is how much? First we will take 1 angle 0 because of no load condition. Mod Z is 0.004 plus J 0.04. Why I am not taking the equivalent of this and this? Because what will happen is it is only asking about Ix. Ix will be supplied by Vs1. Okay. If it were asking about If, If is actually 2 times Ix because If is Ix plus Iy, which both will be equal. Why both will be equal? Because system is identical here and here. Both the systems are identical. Since it is asking only about Ix, so I am calculating Ix. Okay. So this will come out to be 24.9 angle minus 84.29. Now if we have to calculate in actual values, we have to multiply it by base current. So 24.9 into base will be MVA base by root 3 into voltage base. So this will come out to be 3.59 kiloampere. That is your RMS value of fault current. In the next part of the same problem, it is saying instead of three-phase fault, a single line to ground fault occurs at point F on phase A with zero fault impedance. Okay, zero fault impedance signifies ZF is 0. Okay, we need to find RMS value of fault current Ix. It will be 1 by, in case of LG fault it is 3 by mod Z1 plus Z2 plus Z0. Okay, because Zn is also 0, solidly grounded. ZF is also 0. Now it was given Z1 was 0.04. Okay, because in case of symmetrical fault we only consider the positive sequence impedance. Z2 was given equal to Z1, that is okay, and Z0 was given as 3Z1, that is 0.012 plus J.12 pu. Now if we compute the Ix, it will be 5 times Z1 0.004 plus J.04. So how much will this come out to be? This will come out to be 14.925. Let us say 14.92 pu. To calculate the actual value, we will multiply it by base value, that is equal to 100 by root 3 into 400. Okay, so this comes out to be 2.15 kilo ampere. So that is the fault current for the case of a LG fault. Now clearly here current of LG fault is much less than triple L fault. So it is the case where symmetrical fault is the most severe type of fault. Why? Because fault is occurring at the transmission line. Okay, if fault were occurring at the generator terminals, then LG fault will be the most severe type of fault. Moving on to the next problem. It is saying at a 220 kilovolt substation of a power system, it is given 3-phase fault level MVA is 4000 MVA and SLG fault level is 5000 MVA. So clearly here I can see that MVA of the SLG fault is more than 3-phase fault. So line to ground fault is most severe in this case. Now if we neglect all the resistance and susceptance of the system, we need to find positive sequence driving point impedance. Now we know for a 3-phase fault or a symmetrical fault, short circuit MVA is actually S base upon mod Z1 in PU. Now S base can be written as V line to line square by Z base that is VL square by Z1 in ohm. Okay, so this can be the other formula for short circuit MVA. So here I am considering in terms of voltage because we are given the voltage and not the base MVA. So if we equate it, 4000 will be equal to 220 square by Z1. From here Z1 will come out to be 12.1 ohm. Okay, this will be the positive sequence impedance for the bus or for the case of fault. Okay, in the next part of the same problem it is asking the zero sequence reactance. Now whenever we have three impedances, let us say Z1, Z2 and Z0, but we have only two equations. One equation is for triple LG fault, other is for LG fault. So we have two equations and we have three variables. So what to do in such a case is, you will assume that Z1 is equal to Z2. Okay, if ever you fall into such a place that there are three impedances and only two equations, you will assume positive and negative sequence as equal. So this will be equal to 12.1 ohm. Now we know the short circuit MVA for LG fault is 3 into S base by mod Z1 plus Z2 plus Z0 in PU. Again replace S base by VLL square by Z base into Z base. So this will be 3VL square by mod Z1 plus Z2 plus Z0 ohm. So it will be 3 into VL is 220 square by 24.2 plus Z0, which will be equal to 4000. So from here Z0 comes out to be 4.84 ohm. Okay, so this will be the zero sequence impedance. From here you can also see that Z1 is equal to Z2 is greater than Z0. So this is the case of a generator. Hence the line to ground fault is more severe as compared to your triple L or the symmetrical fault. I told you symmetrical fault is most severe when fault occurs on a transmission line because zero sequence impedance is high. Here zero sequence impedance is low, due to which LG fault is most severe. In our next problem, it is saying a 500 MVA 50 Hz 3-phase turbo generator produces power at 22 kV. Generator is star connected and neutral is solidly grounded. So Zn is 0. Its sequence reactance x1, x2 and x0 are given. It is operating at rated voltage and disconnected from rest of the system. We need to find subtransient line current for SLG fault. Now I symmetrical will be 3 by mod Z1 plus Z2 plus Z0. That is 3 by 0.15 plus 0.15 plus 0.05. Here 3Zn will be 0 because Zn is 0. So it will be 3 by 0.35. So how much will this come out to be? This comes out to be 8.57 pu. This is the subtransient line current for the case of SLG fault. Okay, just keep in mind to maintain a factor of 3 here. In our next problem, it is saying a 20 MVA 6.6 kV 3-phase alternator is connected to 3-phase transmission line. Okay, so this is alternator, this is your 3-phase transmission line. Now positive, negative and 0 sequence reactance of alternator are given. Positive, negative, 0. For generator it is 0.1, 0.1, 0.04. Neutral of the generator is connected to a ground through a inductive reactor J.05. So Zn is J.05. Okay. For transmission line, positive, negative and 0 sequence are 0.1, 0.1 and 0.3. As you can see, Z1 equal to Z2 and Z0 is 3 times Z1. All PU values are based on machine rating. A SLG fault occurs at the far end of the transmission line. We need to find voltage of alternator neutral with respect to ground. Now alternator neutral voltage will be I neutral into Z neutral. I neutral is actually 3 IA0 into Zn. So we have to compute IA0. For the case of SLG fault, IA1 is equal to IA2 is equal to IA0, which is equal to 3 by Z1 plus Z2 plus Z0 plus 3 Zn. Now Z1 for the system will be Z1 generator plus Z1 line. Since both are connected in series, their respective sequence impedance will be added. So it will come out to be J.2 pu. You have to separately form the sequence network for each sequence. Z2 generator plus Z2 line. So it will come out to be J.2 pu. Now Z0 equivalent will be Z0 generator plus Z0 line plus 3 Zn. So it will be 0.04 plus 0.3 plus 3 into 0.05. So it will be J.49 pu. So from here IA0 will be 3 by J.2 0.49. So how much will this IA0 come out to be? IA0 will be only this much, 1. So it will be 1 by 0.89. It will be 1.123 pu. Now if we wish to calculate the neutral voltage, Vn will be 3 into 1.12 into 0.05. So 0.15 into 1.12 will be 0.168 pu. To calculate the actual value, we will multiply it by the base Vn will be 0.168 into 6600 by root 3, which will be 640.18 volt. So here we have to take the phase voltage base value because it is not the line to line voltage, rather the neutral voltage. In next problem, it is saying the severity of LG fault and three phase fault at the terminals of unloaded synchronous generator is to be same. Severity is same means IF LG must be equal to IF triple L. If terminal voltage is 1 pu, Z1 and Z2 and Z0 are given, we need to find the reactance for neutral grounding. Now this will be equal to plus 3Zn, and in case of triple L it will be 1 by Z1. So how much is this? 0.25 plus 3Zn 1 by 0.1. So here Zn will be, it will be 0.05 by 3, that is 0.0166 pu. That will be your reactance or the impedance for the neutral grounding to make LG as well as triple L fault having the same severity level. Okay. Otherwise, triple L fault will be more severe as compared to your LG fault. In our last problem, it is saying for the system shown in the diagram given above, what is the line to ground fault on line side of transformer equivalent to? So here it is saying that LG fault is occurring. We have to see the fault here, or we have to refer the fault here. What will be the nature of fault? Now, if you see, this is a delta star type of transformer. In delta star grounded, what is the zero sequence circuit? Here we will keep open the series switch. It is like this. So zero sequence current can flow on the star side, but it cannot flow in the lines of delta. So if you see from the generator side, it will appear that there are no zero sequence current, and IA0 is 0 only for the case of line to line fault. So from generator perspective, it will seem that the line to line fault has occurred in the system, due to which no zero sequence currents are flowing. Hence, if we refer the LG fault on the generator side, it will become line to line fault. Okay. So here you just have to observe the sequence currents from the generator side. Okay. Based on the sequence current on generator side, we can judge the type of fault. So such kind of questions can also be framed which will relate different type of faults. Okay. So only these kind of questions are generally asked from unsymmetrical fault, that is for computation of fault current. And for symmetrical, two type of problems. Ones are conceptual, in which we will be given phasor diagrams, location of fault, and ones are numerical, in which we have to find the symmetrical fault current. So these are the few type of problems that can be framed from this topic. Okay. In the next unit, we will be studying about the stability of the system.